Welcome to another Cram video. This is AP Physics 2. We'll be doing fluid dynamics today and talking about Archimedes Principle and all kinds of things. We'll get started off with what water pressure is, or hydrostatic pressure. And the way you calculate hydrostatic pressure is pressure P is equal to rho GH, rho being the density of water, which is going to be 1,000 kilogram per meter cube. So remember, we're in kilogram over meter cube. And then G is 9.8, and height is actually the depth that we are. So let's say I want to calculate the pressure about right here. We got to measure the height below, which is the depth below the water, and that's what goes there. And then rho and G are constant. Now that's going to be known as the gauge pressure. So if we take pressure total, that'll be equal to the pressure gauge, I'll just use letter G for that, plus the pressure of the atmosphere on it. So the gauge pressure is relative to the atmosphere, but if I want total pressure, I got to remember that there's an atmospheric pressure on it, and remember that's 101,300 pascals approximately. So there you go. So that's how you calculate hydrostatic pressure. Now, what about Archimedes Principle? Archimedes Principle says the buoyancy force is equal to the weight of the substance that the object is floating in, or could be sunk in, the weight that is displaced by the object. Okay, so we have an object here in water, and this is going to be the volume above. I'll just say AB, and this is the volume submerged. The volume submerged is what's equal to the amount of water, the volume of water that's displaced. So how do we deal with that? Well, let's just do a quick free body diagram. Force of gravity, of course, is pulling downward on this, and force buoyancy, I'll just use the letter B, is up. And these two are equal to each other if the object is indeed floating. Okay, so to get gravity force on this object, so the force of gravity is going to equal the density of the object multiplied by the volume of the object. Okay, and then of course multiplied by G. So the force of gravity is going to, when you take density, multiply it by volume, you do get mass, and then multiply that by G. That's 9.8, so that'll give you the weight of the object. So if it's floating, this must be equal to the weight of water being displaced. So force buoyancy then is then going to equal the volume, and I'll put labels on this, of the object, multiplied then by the density of the fluid, and multiplied by G. So these were all of the object here. This is the volume of the object. Now we want to specify this. This is going to be the volume of the object submerged, because the amount of object submerged is going to be what pulls water out of this. Okay, so we can set these two equations equal to each other, and I'll use a better subscript so we can figure this out. So the density of the object multiplied by the volume of the object multiplied by G has to equal the volume submerged multiplied by the density of the fluid, and that would be multiplied by G. So we see that we can cross off the G's there, and we get a proportion. Let's do a proportion, okay, with our volumes on top of each other and densities on top of each other. So let me divide this to the other side. So we get volume of object divided by volume submerged. Okay, so I divided that to the side. I'm going to divide this one to the other side. Has to equal the density of the fluid divided by the density of the object. Okay, so hopefully that helps. Gives us a nice little formula to deal with. Volume of object, of course, is length, width times height. So the length and width this way, and of course if we have a box it'd be going this way. I'll just kind of draw this to help you see that. I'm not really great at art, but here's the length and there's the width. So the length and width of each object, okay, is indeed the same. So we can actually change this to the following ratio. The height of the object divided by the height submerged also has to equal the density of the fluid divided by the density of the object. So it all depends on what you're trying to solve there in whatever question you're being asked to find. Now we'll do one more question or one more idea in this video, then we'll continue later on. What if I have an object completely submerged and I want to figure out what the force normal is acting on this? So force normal is upward. We indeed have force gravity downwards. Okay, but we also have a force buoyancy upwards. So probably a good way of doing it is just saying the sum of all forces in the y direction equals 0 equals force buoyancy upwards plus force normal upwards minus force gravity. And you're going to see that the normal force will be less because some of this object's weight is being held upwards. It's still resting on there, the bottom of the water there, but we're still going to experience less normal force. Now the force buoyancy in this case is then going to equal, remember, the volume submerged. In this case, it's the whole volume of the object, right? Multiplied by the density of water. I'll just put density of water, and then multiplied by G. And remember, the force of gravity on the object is going to equal the volume of the object. In this case, it does equal the volume submerged, multiplied by the density of the object, and then multiplied by G. So you can find force normal then, because you can figure this one out, you can figure that one out, and then they all equal 0, so then you can find force normal. And that's how we deal with Archimedes' principle. We have enough time to consider like a balloon in air and what the buoyancy force on the balloon should be. So again, we have force gravity downwards and force buoyancy upwards. And our calculations, of course, would be, identical that we were doing before. So maybe buoyancy force may not be equal to gravity force, so this balloon may actually go upwards. But we can still calculate the buoyancy force on this object by doing the following. The force buoyancy is going to equal the volume of the balloon, because the whole balloon is submerged in the atmosphere, multiplied by the density, this time of air, and that would be multiplied by G. So the weight of fluid this time displaces the weight of air displaced, and the force gravity of the balloon is going to be found the same way. So again, the volume of the balloon multiplied now by the density of the balloon. I'll just use the letter B here, and then multiplied by 9.8. So if this is a helium balloon, of course, the density of the balloon is going to be less than the density of air. So force gravity is going to be less than what the buoyancy force is pushing on this upwards. So therefore the balloon will go up. And that's about all time we have now. The next video will be coming.